Okay, so welcome back. So last time we talked about measurement-based quantum computation. So I'm going to review the picture briefly and then discuss the topic we didn't have time for last time. It is the blind quantum computation. Then we start with the week 10's topic on quantum entanglement. Okay, so yeah, this is a brief review of the measurement-based quantum computation using cluster states. And we already discussed how you get the cluster state. For example, you are in two-dimensional array and you initialize all the state in the plus state. Then you perform the control Z pairwise and you form a two-dimensional cluster state on the square lattice. And so this is a universal resource in the sense that you can take this resource and then to simulate any quantum circuit you want. For example, this is the one we want to simulate. The first thing to do, you can imagine that you cut out qubit you don't need using the control Z, using the Z basis measurement to remove these unwanted qubit. The rest of qubit form a topology that simulates the circuit. Then we mentioned how you can obtain the arbitrary 1 qubit gates. So this is by measuring qubit along the wire in adaptive way. So you perform a sequence of measurement depending on the previous outcome. The next spin may need to adapt the measurement axis. So in this way, you can create a single qubit rotation. And we also mentioned how you can implement a control NOT gate. It's using a shape like this, and you perform X or Y measurement on these qubits that can be used to simulate control NOT gate. Okay, so that's really the basic idea of cluster state quantum computation. It is also called the one-way quantum computer. Let me just write it here. The reason it's called one-way is you measure these qubit, right? Individual qubit measurement would reduce or decrease the entanglement. And so at the end, all the qubits are measured and there's no entanglement left. So entanglement is the resource. Okay. And so in order to create a universal quantum computation, you need to have at least the ability to create 2-qubit gate. So that means you need to have many wires in order to simulate many qubits, and to have that, the connectivity has to be 2-dimensional. And we also mentioned a higher dimension, such as 3-dimension, can be used to perform high fidelity fault-tolerant quantum computation. Okay. So one very surprising application of this framework of quantum computation is that imagine you have a cloud quantum computer. The question whether you can perform the computation in a secure way is possible in this framework. This is called blind quantum computation. And the picture is shown as follows. So the client sort of prepares some state and then send it to the server, and server entangle that in a specific way, and the client asks the server to perform measurement and tell the client the outcome, and the client then tell the server the subsequent measurement axis. And the upshot is that you can perform computation on these qubits. The instruction of measurement is known by the server, and yet the server cannot figure out the exact computation that is done. So I won't be able to describe the detail, but just to give you an essence, it used this particular state called Brickwork state. It has this structure, it's like a brick on the wall, and so there's some entanglement between some of the qubit above and below, so like this. So the requirement is that these states were not created in the beginning. So the client, in this case it's Alice, prepares some state, not necessarily in the 0+1, but with some arbitrary phase. Could be 0, could be pi over 4, up to 7 pi over 4. And these angles are randomly chosen. So in a sense, on average, the qubit are in a completely mixed state. So meaning identity over 2. And she sent these qubits to, let's say, Bob, who's the server, and he arranged these qubits in this specific way. Of course, Alice needs to know the locations. Suppose that this has already predefined locations. Then Bob entangle these qubits according to the edges, apply the Control Z to all these. Then this is the sort of rotated cluster state because of this. There's some randomness here. It's not exactly the original cluster state. Then what Alice does is she tells Bob this qubit it wants to measure in some basis, this qubit in another basis, etc. And let's say she do it column-wise, and then Bob tells Alice the measurement outcome, and then Alice says, okay, the next column I want to measure in the following basis, etc. And this goes sequentially until the end. She can infer the computational outcome. Okay. So because of some randomness, such as these random phases, and also other randomness. So I won't discuss the detail, but when she tells Bob the axis to measure, for example, the 5' may be what she desired to measure, but she randomly flipped that angle by pi. So basically flip the axis randomly. So there's some randomness there. So initial randomness, and also the randomness R is 0, 1, right? So there's randomness here. Yeah, and then she asked Bob to measure in this rotated basis. Okay, so once she has outcome from Bob, she would continue to do this. And it was shown in this paper that in this way, there are enough randomness from Alice such that Bob cannot infer exactly what the logical computation is. So this is very interesting results, but still not yet realistic in the sense maybe we want to use some quantum computer, but at this moment we cannot send a qubit to Bob, right? Suppose you are running on IBM, that we have done some of the notebook. We don't have access to the real physical qubit, so we cannot prepare this state in advance. But if you're creating experiment, some of these elements could be realized and was actually done in an experiment. So that was the essence. So I won't be able to tell you the analysis of why these randomness are enough for security. But I think at least I can explain why a cluster state on this geometry is universal. So first, we can create single qubit gate. In fact, if you identify a region, that would be somewhere, for example, here is one such region. Right? So there are regions like this that you can use to perform, for example, here. You can perform single qubit gate on this one and this one. So alpha, beta, gamma, as we denoted previously, these are the measurement angle. So the measurement angle, xy, and these are alpha, beta, and gamma or theta. These are the axis direction for the measurement. If you measure in this way, you will get a single qubit gate on this line and also the line below. So for example, you could implement single qubit gates and single qubit gate, etc. And to get the control NOT gate, you can perform in this way. So compared to the parameter, there are a few zeros here. And this has to be measured in pi over 4 minus pi over 4. And by some calculation, you can convince that this is a CNOT gate between this control and this target. Okay, so you can implement control NOT gate in a way that would entangle neighboring qubit. And so these are enough for universal quantum computation. Okay. So yeah, so this is how you compose. Suppose this might be, you have 4 lines and this may representing 4 qubit circuit. So maybe this block is implementing a single qubit gate, and this block is implementing another single qubit gate, and the block in the middle may be representing a control NOT gate, and this could be representing a 2 parallel single qubit gate, and etc. Okay, and you might be able to do another control NOT here, control NOT there, etc. So this is how you compose a gate sequence using these measurement patterns. Okay, so if you're interested in more detail, there's a very nice review article here. Okay, so I want to pause here to see if you have any question.
Yes, so Alice doesn't have any way of verifying whether...
Can you speak louder?
Oh, sure. So Alice has no way of verifying that Bob faithfully carried out the measurement that she told him?
Yeah, that has to be assumed, but one way you could do is you could, for example, use one of the qubit. You randomly use, you could randomly
verify
set some track. So you could set some trap. So for example, you are trying to, you always maybe just flip 0, 1, etc., and you know the outcome will be 1, right? And you know it has to be 1, and you see if it gets flipped.
I see.
I think this technique was also used in some classical computation, but that's one way to do that. Yeah.
Okay, thank you.
Sure.
I have a question.
Yeah.
After computation, how to restore this back to the original state?
Do you have to use another?
Do the operation again?
Yeah. So you have to do an operation, because if you want to use, if you are talking about this blind quantum computation, the server, right? The server has to entangle. So the client sends a single qubit prepare independently, and the server would have to entangle, right? That's the first step. And then you start many rounds of communication of the clients that measure in what axis, and the server tells the result, and then you keep going to the second column, etc. Yeah.
So I mean, if the client want to reuse this part of qubits, then you have to restart it, prepare this state again.
Yeah, so you have to, so for example, in the previous one-way quantum computer, right, this is the why it's called one-way. Maybe somebody prepared this entangled state. It prepared in a way that it's really uniform cluster state. And once you use that, then it's gone.
Yeah.
Like you use up your gasoline, you have to go to the gas station to refill the in this case, the entanglement. So that's a resource. So that's why it's called one way. Okay, and here we are not assuming how we get this resource. We're assuming somebody give us this. Okay, but in this blind quantum computation, at least in this way of implementing, it's required that the server need to be able to entangle to create the cluster state. Okay. Any other question? Okay, if not, then we move on to the main topic of today is entanglement. So we're going to talk about entanglement of quantum states, and we have seen this, right? So the most famous examples are the 4 Bell states. The 4 Bell states, and these states, we know it enable many quantum information processing tasks, like teleportation, which is probably the most famous, or dense coding, etc. So one key feature of these states is that they cannot be factorized. So you cannot write these in terms of A tensor product B. So in this case, we're assuming the qubit are in the position of A and B. Okay, so this could be far away. So we assume this cannot be factorized. Okay. So in contrast, a state like 0, 0, 0 plus, they are in this factorizable form. They are not entangled. So we'll also call them separable. Okay. So, okay, I have a question for you. So I have 2 states, ignore the normalization. Which of them is entangled and which of them is separable, or maybe they are both entangled, they're both separable. So maybe use a raise hand function. Is this entangled? Who think this is entangled? Please raise your hand. Okay, so I don't see anyone raise their hand. Let's see. Okay, and who think the second state is entangled? Yeah, okay, I see more than half of you say this is entangled. Okay, and that's correct. So the first one is not entangled. Let's use the definition. Let's see whether we can factorize them. We can easily factorize this, right? You can verify by expanding that. So it's separable. What about the second one? In fact, this is the one we saw in the cluster state, right? This is actually applying the Control Z to plus plus state. And the best we can do is write it up, plus, and down minus. So there's no further way we can simplify, okay? Okay, but you may say, okay, it's really the case that I have no way to simplify further. Okay, now at least in this case, we can be more rigorous. Let's consider arbitrary 2-qubit pure state in this form in the 0, 0, 0, 1, 1, 0, 1, 1 basis, and the coefficients are A, B, C, D. Okay, suppose it's separable, so that means we can write this in this factorized form, alpha 0 plus beta 1, tensor product delta 0 plus gamma 1. Let's just expand these into 4 different terms, and the coefficients are somewhat related in this sense. So they in the form of ABCD, so they might up to a global phase. So I just represented e to I theta. So you can ignore this phase, okay? So this basically says my A, if this side state is separable, I need to have my A in the form of alpha times delta. B must be alpha times gamma. C must be beta times delta. D must be beta times gamma. Okay, so that's the consequence if we assume it's separable. So this means that it implies that this equality hold if you take A times D minus B times C, you see that all these parameters appear once and they're identical, so it's 0, right? So if it's separable, it means that you take A times D minus B times C must be 0. Okay, at least this holds for, you can see that this holds for 0, 0, 0, 1, 1, 1, 0 plus 1, 1, right? AD is 1, BC is 1, and you take the difference, 0. On the other hand, this state AD is minus 1, and minus this is minus 1. In fact, there's an overall, it's an overall factor, square root 2 squared, which is, so this is minus 1. I think, yeah, I think there's a factor. You have to square this. Okay. So this means that if this condition AD minus BC is 0, that means it's not entangled. So therefore, I can just use its absolute value as a way to indicate entanglement, right? So as in the above case, this 0, square root 0 plus 1 minus, this one has C equal to 2 times 1/2. Okay, so I can say, okay, this has a quantity which we call concurrence is 1. Okay, but for this state, which is the plus plus state, okay, I just make a arbitrary. Okay, let me just correct this normalization. If for the plus plus state, the C will be 0. Okay, so this is just algebra, high-score algebra, and give you this consequence, and also give rise to this quantity called concurrence, right? This has some physical meaning. The concurrence, first you have to look at the time reversal operation for a spin ahead particle. If you have never seen this, this is fine, but the time reversal operation on a spin ahead particle is basically complex conjugation on the wave function given by k and followed by the sigma y rotation. Okay, so if you apply to both qubits, so you apply two of these spin operation and complex conjugation, basically that k puts these complex conjugation everywhere. And then we apply the sigma y. So basically sigma y times sigma y is this. So you basically flip the 0, 0 to 1, 1 and flip 0, 1 to 1, 0, right? And add appropriate minus sign like here. Okay. And concurrent happen to be the overlap of the wave function itself with its time reversal partner. So it's measuring how close they are. So if it's 1, that means like the Bell state, they have concurrence equal to 1, meaning that under time reversal, they are still the same, essentially still the same up to an overall phase. Okay, so, and so for example, we can consider a state which is not maximally entangled, but with some parameter data. So let's say cosine theta 0, 0 plus sine theta 1, 1. And the concurrence, right? A D minus BC, B and C are both 0. So really concurrence is 2 times the product of sine cosine, which is sine of the 2 angle. Right? So you can make a plot. This is concurrence C, and that's angle theta. We know the maximum is when cosine and sine have the same value. In this case, it's at pi over 4 for theta, and this is C equal to 1. That's for Bell states. Okay, so that's one example. Question so far? Okay, so yeah, any question?
Yeah, can you hear me?
Can you speak up?
Yeah, it's my mic. By wave function, you mean the spinner? The psi wave function. You just
Psi.
You say the complex conjugation acts on wave function. The wave function here is the spinner, right?
Yeah, we only talk about the spin degree of freedom here.
Okay, thanks.
Yeah.
So,
but if you also have orbital degree of freedom, you would also put complex conjugation on the orbital part. But the sigma y, you say sigma y acts on spin degree, complex conjugation act on everywhere. Okay.
Okay, thanks.
Yeah.
so the graph, the maximum of C is 2. Yeah, maybe a small mistake.
Oh, this should be 1. It should be 1. Okay, let me just divide it by 2. I don't know why. I will give you this Mathematica code, but it should be 1. I think that maybe I multiply extra 2 here when I put a Mathematica, but thanks. It should be 1. It should be 1. So divided by everything by half. Okay. Thanks. Okay. So that's one way to look at really simple 2-qubit system. But for any bipartite system, pure states, there is a more systematic way to look at its entanglement. So we know any 2-qubit, in this case, the dimension is now NA for particle A, NB for particle B, and these are coefficients, right? These are arbitrary coefficients. So I'm assuming I'm grouping a system, maybe a system into a part which is A and B. And there are coefficient and actually NA times NB coefficient, and I can put this into a matrix. And I can do something called singular value decomposition for any matrix. It's basically decomposed into a part which is unitary. And these are non-negative singular value. And a part which is also unitary matrix. Okay. Then you can use this so-called singular value decomposition to rewrite this, because it was size, but I want to rewrite in terms of singular value decomposition. And I have sum over J and sum over I, and these define the new basis. So new basis. So this is new basis for A because it's using the transformation U, and this is a new basis for B. It uses V for transformation. Okay, and they are orthonormal because taking a basis labeled by I to something that we call it K tilde. This is unitary transformation. So the resulting basis will also be orthogonal and normalized. Okay. So in the upshot, if you know the matrix, the coefficient of the matrix, you can decompose and then rewrite in a more simple way, because the K only sum from 1 to a maximal, possibly maximal, and A or MB, depending which one is the larger. Right. In contrast, if you write in this computational basis, you will need to have NA times NB coefficient. So this is called Schmidt decomposition, which can somehow compress a bipartite state in a more compact form. And if you have more than one non-zero singular values, or in this case, this is also called Schmidt coefficient. If you have more than one, which are non-zero, that means it's an entangled. Right? If you only have one, let's say, if only one sigma k, that means sigma k has to be 1, right? And then you only have the state being k a tensor product with kb. Okay, so this would not be entangled. Okay, and because the wave function need to be normalized, the Schmidt coefficient need to satisfy the square, sum of the square need to be 1. Okay, so regarding how you do these single value decomposition, you can use standard software like maybe in Mathematica or in NumPy. You can do SVD, and I'm going to show you just using Mathematica. Let's say we look at example of this. From our concurrence, we can do AD, which is 0, minus BC. So the concurrence is 1 over 3 times 2, right? So this minus 1 from minus B and C. So 2/3. Using this coefficient matrix, I'm using 0, 1 as a basis. So this is the coefficient, 0, 1, and 1, 0. Okay, I don't have 1, 1. Okay. course, from the concurrence, we know this state is entangled, but can we do the Schmidt decomposition? So basically, if you are using Mathematica, you just say, I take this matrix coefficient and say singular value decomposition. I'm returning the U, B, and W. W representing the singular value, but in Mathematica, this is written in diagonal matrix. Okay, and if you do that, this is what you get. So there's a matrix U and matrix, unitary matrices U and B that tell you the local transformation. And W is a collection of the singular values, diagonal matrix in the diagonal. And so in this case, it would be decomposed into sigma 1, and just say sigma 1, 1, 1, okay, plus sigma 2, 2, 2. Formally, it would be like this. And in this case, if you want to compute the concurrence, it would be, okay, maybe let me write as a 0, and this will be 1. So I can use my previous language. AD will be sigma 0, sigma 1, and times 2. It will be the concurrence, and that's what's here. Okay, and you can verify that this is sigma 1, sigma 2. Their product will multiplied by 2 will be this. Okay. There is also another quantity which is called entanglement entropy, which is used nowadays in many places in condensed matter, in high energy physics. It's basically nothing but taking these Schmidt coefficient, because their square sum to 1. So this defines a probability distribution. So with a probability distribution, you can define an entropy, right? An entropy quantity. Okay, so you can take the probability times the log of the probability with a -1 times that. That's the entropy. It's called von Neumann entropy. This is usually defined as von Neumann entropy. Okay, so and von Neumann entropy of a reduced density matrix, but it's nothing but taking these Schmidt coefficient as a probability distribution, and you do this sum. Okay, but what in other contexts you really encounter here is you have a and B, and somehow you trace over B, you get a row A. From that row A, you define the von Neumann entropy to be the trace minus trace row log row. I'm running out of space. Okay, and that gives you a value of 0.55. I'm using base 2 of log. Okay, so of course this has lower value of a Bell state. For a Bell state, the reduced density matrix will be a identity over 2, so the entropy is 1. Okay, so you can see this has a lower entropy, therefore a lower entanglement value. But you can also see from using the concurrence, it shows you the similar trend. Okay, but maybe let me tell you a little bit more of a partial trace that I use here. So I mentioned partial trace earlier in the course, but maybe it's worth mentioning. Suppose I have the Schmidt decomposed form, like sigma k, k tilde, A and B, two parties. I want to trace over second party. Okay, this is called partial trace. What that means is if you have, in terms of matrix, maybe it's easier. So remember when we do these, we would have A11, B, A12, B, etc. And when we do the partial trace, we basically take the trace of this. It's become just trace of the matrix. That's how you can visualize the partial trace. So this is exactly that, but using a more symbolic way is to take the basis, orthonormal basis of B, and then put it on the left and right, and then dot into that density matrix psi. Okay, K dot into psi, it only bring out a K, right? From the right hand side, it bring out the same K because these are the same K, the coefficient sigma K square because you use the bracket and kit. Okay, and this is basically is nothing but a diagonal matrix. Sigma 1 square, sigma 2 square, sigma n square. Okay, and this new base is diagonal. So therefore, this for Neumann entropy is really just entropy of this. I'm missing a square here. Okay. Consequence is that an entangled pure state is only one sigma, right? Just sigma equal to 1. That means it's pure to begin with, but after the partial trace is still pure. So because the diagonal with only one eminent 1, even if you trace over, do partial trace, you still get 1. So it's still pure. Okay. So in some sense, it's easy to tell whether a pure state is entangled or not. You just do some partial trace and see if it's still pure. Okay. So let me just comment that these separable states, an entangled state, they can be prepared locally. So what I mean is if a state is in product form AB, you can just say, Alice, you prepare a horizontally polarized line and Bob prepare a vertically polarized line. So they can be done locally. For such a state, you just prepare a plus state locally. Okay. But it could also be a slightly more complicated separable state. It could be a separable mixed state or mixed separable state, which is nothing but a taking mixture of this form. So with some probability distribution, and these can be also created locally with communication. So locally and communication. So what that means is, for example, Alice throw a dice and probability 2 prepare H. And at the same time, Bob prepares H. So this is where the classical communication comes in. And with another probability hat, you prepare B. So you can see that this can be created locally, but a entangled state, you cannot create it locally. Okay. Okay, so we have seen how we can quantify entangled state, at least in the qubit case, using concurrence. and in the bipartite pure state using Schmidt decomposition. And so what about more generally, maybe more general states, including mixed state? How do we determine a mixed state is entangled or not? In fact, this is a hard problem, and it has been shown it is an NP hard problem. So generically, it's very difficult to say if a mixed state is entangled or not. But once you know it's entangled or not, how can you quantify? So in general, these are difficult. So we only can solve special cases. So maybe a simple example is maybe more physically, you have two spins that they interact in this interaction. This is called Heisenberg interaction. Basically, the spins are interacting with each other. So this energy is correlated depending on the form of spin and the other configuration on the other side. Okay, so you can solve this. Maybe I could use this as an exercise. I assign an exercise for you to try this. It's really just a 4x4 matrix. You can diagonalize and you find 4 eigenstates and 4 eigenvalues, j, j. 3 of them are j, and 1 is -3j. And in fact, if j is larger, this is called anti-ferromagnetic coupling. So the tendency is you want to form opposite direction. So you see that this singular state, this is the belt, one of the belt state, this is the other. And these two are not entangled, but since they have same energy, you can also form the plus and -1 combination. But this state is special because it has the lowest energy. And that's expected because they are interacting in an antimagnetic way. So they want to sort of pointing in the opposite direction to minimize the energy. Okay. And you can define something called a thermal density matrix. Thermal density matrix. So naturally, you get a 2-qubit in mixed state. That's defined this way. P1, this is really just e to the minus beta h over this trace. Okay, so maybe I want to comment that this example maybe is more for student has that have physics background. For those who probably not familiar with this, maybe you can just regard, okay, I can write this as a thermal density metric as a sort of mixture of a pure state, a singular state with completely mixed states. And I can ask, when is this state entangled? Okay. So using the pure state concurrence would not be enough. Using the Schmidt decomposition would not be enough because they're only for pure systems. So in general, to characterize a mixed state entanglement is not so easy. But this is a simple enough system, one should be able to do that. But first, let's maybe see if we could, maybe for this particular example, can we determine when is this state entangled? Okay, when is this state entangled? It turns out in this particular case, there's a simple criterion. It's called PPT. It's because it's using the partial transpose. I'm going to introduce that, and it's proposed by these two people, Harris and Horodetsky. So the idea is that, so maybe before I continue, I want to pause to see if you have any question. Okay, so maybe if not, let me continue this a little bit. So if I have a separable state, as I said, it's a mixture of product state, right? I can just write this. Row A tensor product, row B, and it could be a mixture. So what I could do mathematically is to transpose the density matrix, right? You know, a density matrix is a Hermitian matrix. Density matrix is Hermitian and also eigenvalues non-negative. So under a transpose, this property should remain, right? They also hold. They're still. It represents a different state, but it still is a valid state, which means it's still Hermitian. Eigenvalues are still positive, right? And therefore, you take another positive matrix and tensor product together, still a valid density matrix. Okay, meaning the eigenvalues are still not negative. This is a simple observation. This operation is called partial transpose. So I'll give you more visualized way to see that. But the upshot, somehow the consequence is deeper than this face value there. Because we see that if a partial transfer of a density matrix is not positive, it must be entangled, right? Because we assume not entangled, this is really logical. If we assume not entangled, and we deduce that it has to be positive, right, after PPT. So that means if it's not positive after PPT, it must be entangled. So that's really the reverse of the condition, right? Okay, so this sounds abstract. So I'm going to do an example. But before that, I want to mention that this is a condition that turns out to be necessary and sufficient for qubit, 2-qubit case, or 1 qubit, 1 qubit. So this is the example. So let me do this example. We have this Bell state. I take this Bell state, I write in terms of density matrix. 0, 0, 0, 1, 1, 0, 1, 1. This is the basis, right? I take this density matrix. So basically, I hope you remember how you do that. This really is taking square root 2, 0, 0, this, and then take that. Okay, and that gives you this matrix. And how do I do partial transpose? It's very easy. You just divide this into a block form and you do transpose on each. When you do the transpose of this return that into here, okay? The transpose basically transpose these. And if you diagonalize this matrix, you see that this is diagonal, this is already diagonal. So 2, 1/2, 1/2. And this matrix here, you give you 1/2 and minus 1/2. So you see that it has a negative eigenvalues. Okay, so we can use this negative eigenvalue to characterize the entanglement. Okay, so we see that it's entangled. You could also define a quantity called negativity. So it's 2 times the sum of the negative value. In this case, it's 1. So we can also say negativity is 1. Okay, any question? Okay, if not, we could actually look at another example. We take this mixture. So I'm doing this in preparation to look back, going to look at the example, the physical example that I show you. But let's take a mixture of the two. So we add a completely mixed state. and it's really just this missing with identity, okay? And you see that this is a matrix. You take the partial transpose, right? Basically it's this, and you diagonalize, basically you only need to diagonalize this part, and you see that there is a eigenvalue which can be negative. So this is negative when gamma is bigger than 1/3. Okay, any question? Okay, so if well, I want to pause here. Any question, because I'm going to turn into a slightly different.
So,
Okay.
Dr. Wei, you say that the thermal state has an entanglement. What do you mean by that?
Thermal state.
Yeah.
Okay, so
Yeah.
let me see. I thought I have some diagram of that. Maybe let me jump forward a little bit and maybe let me see. I thought I have some slide for that. Yeah, okay, here. This is the one, but I don't want to directly talk about this. But maybe the next slide. So this was a thermal state, right? This was a thermal state. And that's the relation of this parameter R to the temperature. So if you plot this concurrence, which I have not introduced, this is the mixed state. This concurrent definition goes beyond the pure state. And we have not talked about this, so, but it shows that at certain temperature, lower than 3 point something, it has non-zero concurrence. Okay, does that answer your question?
Oh, my question is much simpler.
Yeah.
I mean, when you say the problem, you mean the thermal state that has the 2 qubits.
Yeah, that's this state, right?
And they are prepared separately.
No, they are, in this particular example, they're entangled, right? They're interacting.
Oh yeah,
and
yeah.
you just let the system, maybe there are some bath.
Yeah, there is an interacting term. Okay,
There's
thank
a heat,
you.
there's a bath,
Yeah,
and you let the system cool. Okay,
thank you.
sure. I'll go back to where I was. Okay, so yeah, so the question is how to quantify entanglement, and since this is a difficult question, but there are some useful and concept that can be introduced. So I'm going to talk about some notion called distillation, and it's a reverse subject called dilution. And then I'm going to, these are valid for the bipartite case, but I'm going to introduce a multipartite way of characterizing the entanglement that I also studied before. So let me talk about distillation. So basically, you have many copies of psi, which may not necessarily be a highly entangled state. The distillation is like you want to make the entanglement content to be higher. So like you want to distill alcohol from some solutions, And this is basically a similar idea, but it's for entanglement. So there's Alice here and Bob. They maybe share many copies of this, and the idea is that I want to concentrate maybe to small number of Bell pair that I can get, right? Because Bell pair are really useful for teleportation, for dense coding. So even if I start with something that are not so entangled, maybe if I can concentrate to a smaller number of them, and these could be very useful. But the constraint is that I can only do local operation and classical communication, right? So we already indicated what that means, right? Classical communication meaning that the operation can be correlated. Okay, so just think of this abstractly. So it's like you are distilling alcohol, and from this, of course, the alcohol content, the exact content is the same, but it's just in more dense, maybe less water. So you can define a quantity called entanglement of distillation. So distillation defined as the number of Bell pair that I can distill at the expense of initial M pairs of not so entangled state. And so this definition is in the limit of many copies of psi. So this is conceptually defined, but it's very difficult to calculate. So just as a picture, so this is like the entanglement content is like you have k pairs of psi, which is equal to k pairs of Bell state. So just if you can remember this picture, then would be helpful. It turns out for pure state, this quantity is exactly the entanglement entropy that we defined earlier. It's really, but I don't have time to show you exactly that. I will give you a rough idea of how to see that. Okay, I don't need to go to this detail of partial trace and entanglement entropy. I already mentioned that. Okay. So, but I want to give you an example. I think this example is highly instructive. I'm going to use two pairs. So you see that psi equal to cosine 0 plus psi 1 1 as indicated previously. Now this is now correct. Yeah, this is now correct. If theta is not 1, pi over 2, right, pi over 4. This theta pi over 4 here. If it's not pi over 4, then the entanglement is low, right? So it could be, for example, 0.63, etc., right? As some small angle than pi over 4. This such an entangled state cannot be directly used for teleportation, right? So, but if I have two pair of these, can I do something useful? Can I distill a higher entanglement? So I write the two pair in and label them with particle number. So 1, 3 is Alice side using red, and 2, 4 are on Bob's side, and I have two copies of this. And I just do it mathematically, just expand the product of the two, and I have 4 particle state, and with these coefficient, cosine square basically is cosine coefficient of these 0, 0 state, and there's also 1, 1, 1 state. In the middle, you have cross term that has 0, 0, 1, 1 plus 1, 1, 0, 0. This is probably a source for getting a Bell state, right? So can we do local operation, and maybe with communication, can we distill a Bell state? So that's the setup. Any question? I want to pause for you to think about the setting. I have two pairs of not necessarily the high entangled state, it could be a low entangled state. And I want to see if I can operate on these two pairs collectively and also locally. Can I distill a Bell state? Okay. So here is how to do that. So because Alice has the particle 0 and 3, she can measure the total number of 1. Right? In this case, that's 0. This is 1. This is 1. That's 2. Two numbers of one state, right? In this case. If she can perform such a measurement, I mean, she could in principle. If she gets 0 or 2, then she basically project to this or project to that. And you see that 0, 0, 0 or 1, 1, 1, 1, not useful, right? Not so useful. But if you get, if she gets 1, she collapse to this wave function, and you get this middle part. Okay, the probability to get that is the square of this. Okay. So if she get the outcome k equal to 1, that means I can get this entangled state. It's almost like a Bell state, but it's 4 particle. So can I do something collectively to extract a Bell state? So that's the question. So yeah, we've seen that the state is in this 4 particle state, but our goal is to get a Bell state like this. Because she has particle 0 and 3, Bob has 0 and 2, so they can perform local. So this really locally on their own particle. Assume that they can perform this unitary. I mean, you can see that this is unitary. This is like an X here, like identity here. But the action is that I want to apply U so that 0, 1 turn into 0, 0. And 1, 0 turn into 1, 1. And this is one example. The consequence is that if I perform this operation on both sides, so this is why we need classical communication, because Alice has to tell Bob that we have to do this operation. Okay, so if you do that, so 0, 1 turn into 0, 0, so 0, 0, 0, right? So, and 1, 0 turn into 1, 0 still, it doesn't change. So you have 1, 0 and 1, 0. And you see that particle 3 and 4, they are disentangled from 0 and 1 and 2 particles. So they can be thrown away, and therefore you get a Bell state. Okay. So, and if you consider this procedure that I tell you, but for many copies, basically you are measuring the number of 1, right? You're measuring number of 1. If you imagine you have more copies, there are more outcomes, and you can show that in the large number of copies, this is actually the entanglement entropy that I showed you earlier. Okay, and so this part is what I can show you in more detail, but you have to trust the conclusion. Okay, any question on this protocol? So at least I hope I illustrate what I mean by local operation, like these local operation only acting on his or her own particle. But there is a communication, like classical communication saying, okay, you should also do this operation. Okay.
And
yeah.
in the sense of distillation, we always kind of transfer the entanglement from one 2-pair to another 2-pair. Is that?
So the idea is you have in this case, in this example, you have two pairs, and you want to distill to a higher entangled state, right? And so that has to at the expense of losing some particle, right? You cannot, yeah. So you want to concentrate. You want to concentrate the best to just a limited number of particles. It doesn't matter which one, right? I could choose to disentangle 1 and 2 from the other, and 3 and 4 would be entangled, right? You can imagine doing a slightly different one, right? This is 0, 0. If I turn this 1, 1, 1 to 0, 0, then I can disentangle them. So, but the goal, yeah, go on.
Sorry, and that's necessary in the sense of the entanglement trend.
Yeah.
But wasn't there like embezzlement?
What do you mean by embezzlement? We're going to discuss something called catalysis, but that's in the transformation. But maybe you can wait until we get to that.
Thank you.
Okay. So this is called entanglement of distillation. Okay. But there's also the reverse concept. Like, it's like I have a really high percentage of alcohol, but I want to make maybe a diluted one so I can get many bottles. Maybe this will be for the purpose. You get 90% alcohol. You want to dilute that into 65%, so you can have more bottles for people to use to sanitize, maybe against the COVID-19 viruses, like that. And so this is a resource, but it's shared between Alice and Bob, but they want to distill somehow a lower entangled state psi, but with more copies N than K. And so this entanglement cost, of course, is defined in this way. This is the initial Bell pair over the many pairs of psi. Okay. So this is also the picture, but it just the scale is changed to EC. So previously I was using entanglement distillation, so the scale is a bit darker. I use ED, entanglement distillation here. Okay, but that's the reverse process I'm talking about here. So how to do that? You can actually do the dilution process using something called first using something called compression, and then you use teleportation. So the idea, I will not be able to explain quantum data compression today, but I'll explain maybe on Wednesday. Suppose you can prepare k copies of the psi. You can prepare, Alice prepare this. So Alice prepare psi locally. And what she does is she will do some compression. So as indicated here, okay, she has many copies of these. She compress into fewer number of qubit K. Then she used the K Bell pair to teleport to the other side, Bob. So maybe the idea is you create these locally psi, and then you compress with a fewer number. So they're N here and they're N K here. Then use teleportation. Teleport means that it was originally at A, then teleport to B. And we use the same number K for teleportation. And once Bob obtained the teleported particle, he decompresses. Okay, so this allows you to achieve the rate K over n. Okay, so I won't be able to talk about this, but next time I will explain that. So this means that the process are reversible, right? So distillation and then dilution, they're sort of convertible. So you can convert reversibly from side to Bell pair and Bell pair back to side. Okay. So any questions? Let me see. We only have a few minutes. So maybe what I do is I go to my mathematical notebook. Can you see the notebook or it's not yet? I have not.
No notebook seen.
Okay, so let me see. New share notebook. Can you see that?
Yes.
There is the formula for concurrence, so which I will explain next time. But this is generate to mixed state. So you see that there's a YY, which is the time reversal operation, the spin operation, and also have the conjugation. And it can be generated to mixed state, but in mixed state you have to get this density matrix. That's the transform, so time reversal density matrix. And you have to do an eigenvalue for the original one to the time reverse one. So remember when we were doing the pure state, we only need to do the inner product, but this time we need to do the eigenvalues. When you get eigenvalue, you take the square root of that, and you take the largest one minus the sum of the remaining. Okay, and that gives you the concurrent. But since I did not explain that, I will explain that more detail. But this is the function. This is the Bell pair, right? I turn that into a density matrix, and I use my function to compute the concurrence as one. This is the Burnham state that I told you, which is a mixture of Bell pair with some identity, right? So identity matrix. And I use my function and calculate as a function of this parameter R. That's how the entanglement scales. So R equal to 1, meaning that it's the maximal entangled state. The Bell state has concurrence 1. But at a value of 1/3, it becomes non-entangled. Okay. You could also use the singular state. It just differs by where the matrix element 1 and a half and minus a half is. You check its concurrence is 1. This is where I do the temperature. So remember there is the formula of the parameter R related to temperature. So this is where I set the temperature. Then I take these mixture and plot the concurrence as a function of the temperature. Okay, the temperature is in unit of the coupling J over the Boltzmann constant. Okay. This was a plot that I used for the polynomial entropy of these cosine theta 0, 0 plus sine theta 1, 1 state. So if you remember this, that's the plot that I have, and it should go up to 1, and also the concurrence should go up maximally 1. This part was the Schmidt decomposition using singular value. So remember, this is the square root 1/3 of the coefficient, right? 0, 0, 0, 1, 1, 0. This is the matrix. That's the matrix form. This is really what I said earlier. I just say, okay, do singular value decomposition, extract the U, V, and W. And W is a diagonal matrix. These are the singular values. And U and V are local transformation. Okay, but it has these values. It's like a rotation. This is cosine and sine, and some angle minus sine. This is just a rotation. So I'm just computing the entropy of that, and I evaluate its numerical value. It's 0.55. So that's what I have in the slide. So any questions on this? I can quickly go back to the slide. We're running out of time, but let me quickly go back to the slide to where I have those. It should be earlier. Okay, this is where one of the example, right? On the example of the concurrence. I don't think I show this one in the. I don't think I show that one. But the later plot. Yeah, okay, it was later. Okay, somehow the PowerPoint was frozen. Okay, so any question? Will the computer recover itself? Yeah, so this is where I make the plot of the entanglement formation, but using sort of the concurrence. But that's here. Okay. And I think the Schmidt decomposition was earlier. Maybe here. Yeah, so this is where the Schmidt decomposition. This is the same example, okay? Okay, want to pause and stop here to see if you have any question. Okay, if not, and then we continue on Wednesday. I would finish the discussion of entanglement and then also discuss this quantum data compression. Okay, see you next time.
Thank you.
Thank you.
Thank you.
Thanks.